So my name is Jaebum Jung, and I'm working in the Wolfram Research. And there is Yan Zhao that will give some portion of my talk today. And the title of the talk is Advance in Graphs and Network. So I'm mostly talking about some enhancement in the recent version of Mathematica in graph and network, also giving some new functions for upcoming version of Mathematica and some future plan. So first of all, I will start with multigraph. And this is not new. So as you know, I think if you are here, you're probably a little bit familiar with the graph. So multigraph is multi-edgy, like here, the example here, we have multiple edges 3, 1. Here, 1, 3, 1, 3, 1, 3. So far, so good. It looks nice, and we know this all the same edges. And now we want to distinguish these multi-edges by giving different labels and see what happens. The thing is, now it's showing all first instead of this one second, third. Why is that? It's like a multiple edge like twins, right? Sometimes this all looks same. So Mathematica try to giving some different quantity first, third, second, but he don't know who's who, so he decide to little bit fair. So giving same thing to everyone. So this is what happens. So because if you have 3, 1, 3, 3, 1, how do you know? So in the new version of Mathematica, okay, so here's the 3 edges, 1, 2, 1, 2, 1, 2. So what we gonna do is, oops, you see here some kind of tag. So we introduce tag. So each edge can equipped with tag, which distinguish the multi-edges. So how we do that? So here's the traditional edge, undirected edge 3, 1, and we introduce third argument, which called tag. So in this case, tag of this first 3, 1 is me and brother. Now we can know, we can give some identity. So for example, like here, now we can label, giving the different label for same edges. It's not exactly same. It has a tag now. So here, this is one of the way to defining the tagged multi-edges and giving some identity. And if you don't like just adding tag for each edges, we have some new function to help you define. We call, oops, what happened? Oops. Okay, I have to switch my slide. There are some things going on. Let me just see. Sometimes, sorry about this. Okay. Yep. This should be fine. Okay, now we have better notebook. So we call edge tagged graph. This is function. So what it does is it's same as graph. So like it's same as graph input formula. So label 3, 1 first, 3, 1. We didn't specify tag, but if you use edge tagged graph, it automatically giving tag to each edges. So now you see here, and like even you can specify different colors. And for example, if you just see I will show later. Okay, and then, so right here. So edge tagged graph 1, 2, 1, 2, 2, 3. And you see the difference. If you pull out the edge list, now you see tag for each edge. So it's automatically given to input edges. And we have some companion, the function related to edge tagged graph. saying H tagged graph Q. So it returns true whenever your graph is tagged. And H tags giving you list of H tags, the position is correspond to H list. And another usage of H tags, 1, 2 mean between vertex 1 and 2. It giving the list of tags, H between 1 and 2. In this case, 1, 2, 1, 2. Yeah, we have 2 H's, so you got 2 H tags. And you can raise your hand if you have any questions, short questions. And another function here is index H tagged graph. So index H tagged graph also create H tagged graph, right, like this. But the difference is you just need to think about the relation between graph and index graph. What index graph does is it replaces each vertex to index. Like if you have graph with vertex ABC, if you apply index graph, it converts ABC to 1 to 3. So index H tagged graph convert H tags to index of H's. So here, if you do just H tagged graph, as you can see, the tag is 1, 2, and this one is 1. So if it's different H, it always starts from 1. And H tags 1 to 1. But if you apply index H tagged graph to graph, it looks same graph. But if you pull out the H list, now you see 1, 2, 3, the tags, the following index of edges. And H tags now is 1, 2, 3. So depends on your workflow, you can either use H tagged graph or indexed H tagged graph. Okay, next thing is inheritance of annotations which used to be properties. So what it means is now we have some graph with nice style, Peterson graph. And previous version, some of the functions, some operation or constructor, if you apply the function, G has that nice styling, but this is in version 11. You got the spanning tree, but it doesn't contain any the property annotations from original graph, right? This one G we have in the front. No, not this G. So for example, let me just learn this again. This is weighted graph. But this spanning tree actually remove the edge way. It's automatic. No, I have to learn this in version 11, but I accidentally learned this in 12. And this is kind of sneak peek. So in version 12, same graph. And like you just see, all the function and constructor or some operation will inherit the annotations of original graph, like here, all vertex shape and coordinate, everything, and edge way. And here you can apply the options. In version 11, some of the graph function doesn't even accept the additional options. And now we apply this principle, inheritance, to all of the function in the graph. So you can specify any option, and you can just get the options from the original functions. And it's not just preserving the annotations. We also select if we want to preserve option or not. So this is some usage, how we do that. So for example, if you do subgraph, you see all the annotations is preserved. But like I don't want to do that for some reason, efficiency-wise and something. Then you can say annotation rules, none. Then it just remove all the options from the original functions. So it doesn't carry any So if like it will not have empty options. And also, you say none, but I also want to carry some of options or annotations, like edge style and vertex coordinate. Then you can say edge style inherited, vertex coordinate inherited. Then you just inherit the edge style and vertex coordinate. So there are those combination every possible. For example, like here, you just want to edge style lead, except 3, 2, directed edge 3, 2. So in this case, you see this is 3, 2. It just only this one inherit the original, the options. And other things in new version, we introduced some of new predicate. So like a vertex weighted graph Q and edge weighted graph Q. So we used to have weighted graph Q, but that function return true either graph has vertex way or edge way. It doesn't, even when it's returned true, you don't know which way the graph has, like vertex or edge. So to distinguish that we now have vertex weighted graph Q, it only returns true when graph has vertex way. So this graph only has edge way, so you got the false. Same thing for edge weighted graph Q. False. This is little function, but sometimes you need it, and it's very useful and fast. And new vertex labels. We introduced some automatic scheme for labeling position. So this is what we used giving. So when it's automatic, we always set the vertex labels after above. This is the position, like you said. But in new version, for like a circular embedding, we placed it outside of a circle, so giving more visibility. And even like for spring electrical embedding, you see the difference? Instead of it's above, it tried to check the local neighbor and place the vertex, the label, which have most space. So like here, right? So giving a little bit more visibility for labels.
So what about label 7 there? It's across an edge. Could it not
Yeah, but this edge is not the part of, so this is probably 411, right? So it only see local neighbors.
You're saying the edge there is 4 to 11, not
Yeah. I expect that, yes. So yeah, it's a local scheme in this case. I mean, you can make global scheme, but that take more computation, and yeah. You don't want to spend like an hour for label placement in general. And some new layout, like a gravity embedding. So basically what it does is for graph, we just put some center gravity, and do the spring embedding, the energy-based embedding, and make some nice graph. So all the, it's going to in the center. And new plot themes called index labels. This is like a text in textbook. We see this kind of plot theme a lot, so we just make one. So I just show one, but that doesn't mean we end here. We will introduce more plot theme later. So this is like another constructor max connectivity graph, and this one, the Jan will introduce about these new functions.
Yeah, this is a mesh connectivity graph. So mesh connectivity graph is given mesh. We want the mesh cell, the connectivity between the mesh cells. So when is the dimension is 0, actually this is the points connectivity by lines. This is the except the dimension 0, then we'll give it a graph, the cell's dimension d. That is share a cell of dimension d minus 1. So here we also can give the like if there are two cells in the different dimension, one is from d, one is from e, then these two cells are connected if they share a dimension r. So let's see small examples. So this is a mango mesh. So we want to find the connection, the point connection by lines. So we when the dimension 0, we used the same vertex coordinate for the graph and for the mesh. So here we want to find the connection between the cells, the faces, and the points, and they share the same lines. Then it will be connected. So this is what we get the graph here. So let's see some. So let's see some example here. Given mesh, so this is the face. Okay, so I want to find the adjacent faces around this face. So we can first compute the face connectivity graphs. So compute it. Then we get this is graph. Then we because this is a graph, so we can use the graph function like the adjacency list. So get here, so we can see it's very easy. We get the three the polygons adjacent to these cells. So another new function is the I will talk about is the expression graph. So expression graph accepts the expression, so any expression from the Wolfram language. Here is a small example here. Oh, what? Why is it here? E?
It's clear A and B. A.
Again?
B and C.
Come on.
B and C.
Okay. Okay, B and C, whatever. Finally, okay. So this is expression. So we can get the tree graph here. So but from here we could not see any sub-expression. So if we want to see the sub-expression, we can use the vertex labels automatic. Then here we will see the all the sub-expression, like here a plus, the b power of the cosine things. So sometimes, okay, we don't want to expand the cosine sum expression, so we can use the sum form. Any expression match this form, it will be a leaf. It will not expand. So can here. You can see here the cosine things not expand. So here we can use the limit the level of the trees here. So just one level. So here I just give some example like any expression. So we can use the mesh region, graph 3D, and like the video plot. So we will get some okay, complete trees. Yeah, I think that's what I did. Go ahead. Yes.
So like I said, I will just giving some simple example that interaction with graph functionality and other area. So this case is using the graph functionality to others. So like a molecule, and we have molecule graph. So we can convert the molecule structure to certain graph, and using checking the matrix plot of this distance matrix or something, and even find position of that and apply this position to molecule graph to find the shortest path between the atoms. And this is like using this path we found, we can get the bond list. So this is one simple example how we used graph functionality to other area. And next example is another direction, the opposite direction, what I mean. So in this case, we have graph, and using optimization functionality, we find the max cut problem. Solve max cut problem. So semi-definite optimization is kind of new optimization function. And then doing some computation, we can find the maximum cut. And using that result, we just plotting that max cut communities. And so what's next? We are kind of divided into area, learnability, usability. This is kind of vague future plan. So learnability, what it means is we will improve, and we are improving right now, the documentations. Not just graph and some discrete mathematics. So we kind of adding more examples and improved, and giving some easier idea and more application in the documentation. That's what we are doing also. And we're gonna make more courses. So it's more like in-depth than documentation. Even like tutorial or some Twitch talk, all those things. And usability. So we're gonna keep building utility functions. For example, like a vertex-weighted GraphQL is one of the small utility function, but that giving some more useful to users. And large graph, what it means is like large graph means some graph we mathematics cannot handle because it's too big. So in that case, one of our plan is called like out of core graph. So you store your graph not in the Mathematica, in your for example hard drive. And we just taking some portion of it and do computation. You have object in the Mathematica, but that object is connected to out of Mathematica, so we can handle some large graph. That's another plan we have. And more, so we are not restricted to utility function and logic graph. We will have new functions and also new improvement of existing functions. So that's it for today. And do you have any questions? Yes?